Hello and welcome to our next video for our module. So this is section 9.2, and we're going to go a little bit deeper in this entropy concept and do a little bit of math in terms of entropy. So let's get right into it. So again, consider that if we want a spontaneous or a thermodynamically favorable process, there is going to be an increase of entropy of the universe. Now that's not our system, that's the universe. So the energy that we have in the universe is constant, but entropy is not. Entropy is constantly increasing in the universe. So the change in entropy in the universe is going to be equal to the change in energy of our system and the change of energy of our surroundings. Sorry, entropy, excuse me. So our standard entropy value, so remember, this is occurring at 298 K and 1 atmosphere. Those are the standard conditions. Remember that because that's going to be important for some problems later. The units that we use for S, or entropy, is joules per Kelvin. Entropy is a state function, so we can calculate it using the standard entropy values of our reactants and products, just like what we did with enthalpy. Okay, so the sum of our products, okay, the number of moles of our products times the standard entropy of our products minus number of moles of our reactants times the standard entropy of our reactants. Okay, that will give us the change in entropy of our reaction. So this should look familiar. This is exactly what we did with our standard enthalpies. Okay, so now we're gonna look at one example and then I'm gonna have you work on one on your own. So for this first one, again, this is at standard conditions, 25 degrees Celsius. So Al2O3 plus 3H2 yields 2Al plus 3H2O. So notice how our solid things have lower standard entropies than our gases do. Okay, that should make sense based off of what we talked about in our previous section. So how are we going to work on this? So remember that our delta S for the reaction is going to be equal to the sum of our products minus the sum of our reactants. Okay, so let's put it all together. So our products, we've got 2Al. So this would be 2 moles times its standard entropy, which is 28 joules per Kelvin times moles. I didn't write those units in just to save some space. Okay, plus 3 moles times 189 joules per Kelvin times moles. So the moles times the joules per Kelvin over moles, the moles will cancel out and leave you with just joules per Kelvin, which is what I've demonstrated down here. Okay, so those are our products. We add those all up and we end up with 623 joules per Kelvin. Then for our reactants, we have 1 mole times 51, that's our aluminum oxide, plus 3, that's our H2, moles times 131 joules per Kelvin times mole. Per mole. That is going to add up to get us 444 joules per Kelvin. So when we put these together, 623 minus 444, we end up with positive 179 joules per Kelvin. Right, so now practice number 2, why don't you try that out on your own? So do the same thing that you did before, but for this, you will use different values based off of a different reaction. Okay, so you'll be able to find the answer in the notes in this document, and that's all for 9.2. So up next is going to be 9.3.